In this video, we will get acquainted with a powerful quantum communication operation whereby quantum states can be transported from one place to another by consuming a Bell pair and two classical bits. This fantastic quantum communications primitive, impossible with classical communications, is called quantum teleportation. In this primitive, we have two parties, blue and yellow. Blue will transmit an arbitrary quantum state, whose state might even be unknown to itself, using a quantum channel and two classical bits. Even though currently experimental physicists are still struggling to implement it, in theory it's quite straightforward when we introduce the means to create a Bell state, to perform a unitary operation, and to analyze a Bell state, the latter being performed through a so-called Bell state analyzer. A Bell state analyzer, analogous to a qubit analyzer, allows one to determine which of the four Bell states are encoded into a two-partite system. Since the Bell states form a basis for any two-partite quantum state, the Bell state analyzer performs a projection onto the Bell basis, which, as we will see, allows quantum teleportation to take place. To set the stage for quantum teleportation, we can start by reviewing the major components of our operation, the Bell states, and how to create them. As you will remember, there are four maximally entangled two-partite states, which are called the Bell state due to John S. Bell, who used them in a work in 1964 to counter Einstein's argument that quantum mechanics might not be complete. One important feature of the creation of these Bell states is that they are entangled, and thus an entangling operation must be present. This is the role of the CNOT gate after the application of the Hadamard gate on the first qubit. It is also interesting to note that it is possible to go from one Bell state to any other through the application of a unitary operation. As we can see for phi minus, psi plus, and psi minus. Provided one knows which Bell state has been created, determining whether the creation was successful, or in other words, validating it, is straightforward. A projection onto the known Bell state followed by Z-basis measurements yield positive eigenvalues as results and validates the Bell state creation. In the general case, however, the input bipartite state is not known, so the previous strategy is not useful. However, if the Bell basis is transformed into the computational basis, a pattern in the Z-basis measurement results can be identified. Therefore, by matching the resulting pattern with the expected pattern for each Bell state yields the projection result, thus composing the Bell state analyzer. For teleportation to take place, we need first to prepare a Bell state. We also prepare an arbitrary qubit, the one we want to teleport. We then send the prepared qubit to a Bell state analyzer together with one of the parties of our Bell state. The joint quantum state of this bipartite system, part prepared qubit, part Bell state, is projected onto one of the Bell states, producing a resulting pattern. The result, encoded into two classical bits, can be used to select which unitary transformation will be performed on the remaining party of the initial Bell state, such that finally we recover the prepared qubit. It becomes clearer when we follow the mathematical steps. Let's do that. First, the full joint stent can be written, with the arbitrary qubit and the created Bell state. This can be rewritten for clarity. Second, the Bell state analyzer is introduced, and the expression can be twice simplified, revealing the initial qubit state, but now in the yellow path instead of in the purple one. It is also important to note that it comes accompanied by different unitary operations, depending on the z-basis measurements of the Bell state analyzer. This means that the qubit will be recovered in the yellow thread only when the result of the projection, and thus which unitary operation to perform, is known. Now we have our full teleportation protocol set up.